Hey everyone, and welcome to this explainer. I am so incredibly excited to be your guide today because, well, we're going to unpack one of the absolute most dynamic and dramatic objects in our entire night sky. We are pointing our telescopes at Caldwell 27, which you probably know better as the Crescent Nebula. Now, this cosmic marvel was first discovered by the legendary astronomer William Herschel way back in 1792. But as you'll see today, modern astronomy has peeled back the layers of this nebula to reveal a story of stellar violence and, frankly, chemical creation that Herschel literally could never have imagined.
I mean, just take a look at this incredibly fractured, glowing structure. It is absolutely mesmerizing, right? What you're seeing is a sprawling, chaotic web of highly fragmented gas. But actually, scratch that. This isn't just a pretty picture. It's a crime scene, and it introduces our main mystery for today. Why exactly is this beautiful stellar structure so violently broken apart? Like, what kind of immense cosmic forces could shatter a nebula into these chaotic, glowing clumps?
Now, what's really interesting about this is the sheer mind-boggling scale of the crime scene. Caldwell 27 doesn't just sit in our cosmic backyard. This massive shattered nebula is located a staggering 5,000 light-years away from us, nestled deep within the Cygnus constellation. So to put that into perspective, the light we are studying right now, it left that nebula right around the time human civilization was just starting to figure out written language. How wild is that?
Okay, let's dive into this. Here is our roadmap for solving the mystery. First, meet the Crescent Nebula. Second, the three-wind cosmic collision. Third, anatomy of a nebular shell. Fourth, chemical clues of stellar death. And finally, number 5, the million-degree interior.
Section 1. Meet the Crescent Nebula, the engine inside.
To truly understand what's happening in Caldwell 27, we have to look past all that beautiful glowing gas and identify the engine sitting at its absolute center. The entire structure of this nebula is dictated by one incredibly powerful object, a star known as WR-136. So WR-136 is what astronomers call a Wolf-Rayet star. Basically, a Wolf-Rayet star is this very rare, very late evolutionary stage of a truly massive star. We're talking about stars that start their lives with more than 30 times the mass of our own sun. In this late stage, the star becomes highly active. It's shedding its outer layers through these extreme stellar winds and massive mass loss. This dying giant is the exact engine powering the whole hydrodynamic and chemical display of the nebula.
And this brilliantly illustrates the basic spatial layout we're dealing with. Working from the inside out, you have the intense post-shock wind from the Wolf-Rayet star itself forcefully pushing outward. Above that, you see those dense clumps of gas getting photoionized, basically blasted by the intense ultraviolet radiation from the central star. And then, right at the outer edge where it interacts with the surrounding interstellar medium, there's a thin, continuous skin of gas glowing in a very specific wavelength of light. It's a highly structured system, completely driven by that relentless outward pressure.
Section 2. The three-wind cosmic collision, a violent timeline.
So how did this incredibly complex structure actually form? Well, it turns out the Crescent Nebula is the direct result of WR-136's own past life phases physically crashing into each other. It's like a massive cosmic pileup. The star evolved through 3 distinct stages. First, during its main sequence life, it swept up nearby interstellar material to form a massive invisible bubble. Second, as it got older, it became a red supergiant, shedding its outer layers in a dense but, relatively slow-moving wind. And finally, stage 3, it transformed into a Wolf-Rayet star, blasting out a massive, insanely high-speed wind.
Watch closely as we step through a simulation of how this physically played out. We start right here with the initial stage. Inside that massive main sequence bubble, the star has already shed its red supergiant material. At this point, that red supergiant shell is just resting calmly, expanding outward relatively undisturbed. It's kind of the quiet precursor to the storm.
But then, boom, the star enters its Wolf-Rayet phase. As the simulation progresses, we see the incredibly fast, modern Wolf-Rayet wind shooting outward. And because it's moving so much faster than the old red supergiant material, it aggressively catches up to it. It literally slams into the older, slower shell from the inside out. The impact is just devastating. Notice how the immense pressure causes the outer boundary of that older shell to become incredibly unstable. It starts to buckle, warp, and violently fracture. The smooth shell is entirely losing its structural integrity under the relentless hammering of that fast stellar wind.
Let's move forward and see how this builds, right up to the climax of the collision, a complete physical blowout. The inner bubble breaks all the way out through the outer shell, shattering it into pieces. What is left behind isn't a smooth bubble at all, but the heavily clumped, highly fragmented remnants we observe in the sky today. It is a stunning visual of a star basically destroying its own past.
Section 3. Anatomy of a nebular shell, clumps versus skin. Bringing it back to the present day, we can analyze the physical evidence of this historic cosmic collision using the incredible power of the Hubble Space Telescope. When we look at this, we see a stark visual contrast using two different filters. Looking at hydrogen alpha light, we see those dense, chaotic photoionized inner clumps, the shattered debris of the old shell. But then, looking at light from doubly ionized oxygen, or O3, we see something completely different, a smooth, continuous, shock-heated outer envelope wrapping around the whole structure.
So the crucial point is that by looking at different wavelengths of light, we are actually seeing distinct physical pressures and temperatures battling it out right at the nebula's edge. The fragmented clumps are dense material getting blasted by UV light from the star. Meanwhile, the continuous skin is a thin veil formed by the outward shock wave cooling as it rams into the surrounding space. It's basically two entirely different physical environments existing right on top of each other.
Section 4. Chemical clues of stellar death. The nucleosynthesis fingerprint.
Let's shift our focus from the physical shape of the nebula to its actual chemical makeup. Utilizing incredibly deep spectral data gathered from the giant 10-meter Gran Telescopio Canarias and the Magellan Clay telescopes, astronomers found some massive chemical anomalies. Specifically, nitrogen and helium are highly enriched, while oxygen is heavily deficient. Plus, the ratio of neon to oxygen is way lower than expected. Why does this matter? Well, because these specific chemical signatures are the smoking gun. They prove without a doubt that this gas isn't just random space dust. It was processed and cooked deep inside the nuclear furnace of the massive progenitor star before being violently ejected into space.
These nucleosynthesis data charts map out those exact elemental abundance ratios. And the spectacular thing here is that these specific chemical patterns match up perfectly with evolutionary models for stars that begin their lives with somewhere between 25 and 40 times the mass of our Sun. The chemistry absolutely confirms the physics.
Section 5. The million-degree interior, X-rays and thermal evaporation.
Now we shift from the visible optical shell, the glowing clumps and skin we've been looking at, to the invisible, unbelievably hot gas trapped inside. Deep inside that fractured shell filling the interior of the nebula is a low-density gas that is emitting X-rays. And the temperature of this gas? It is over 2 million Kelvin. Just let that sink in for a second. 2 million degrees. It's a pocket of unimaginable heat trapped right in the absolute center of the shattered stellar debris.
But where does this 2 million degree gas even come from?
Well, as the Hubble Space Telescope observations note, this material is probably the result of thermal evaporation of nebular shell material into the post-shock stellar wind. What that actually means is that the intense heat from the central star's wind is vaporizing the inner edges of the nebula itself. It is literally boiling those cool, dense clumps directly into the hot, invisible wind. It is an amazing cosmic recycling process happening right before our very eyes.
And that brings us to the end of our forensic journey today. We've seen how the violent death of a single massive star creates incredible structures and very specific anomalies in carbon, nitrogen, and oxygen. Which leaves us with a pretty profound question. If the violent death of a single massive star creates these exact carbon, nitrogen, and oxygen anomalies, how much of the very chemistry that made us was born in a collision like Caldwell 27? It's definitely something amazing to think about the next time you look up at the night sky. Thank you so much for joining me on this explainer, and keep looking up.